If you've worked with a computer for some time, you may have heard that it's all ones and zeros. But is that still true today? And if so, why? Well, the short answer is yes. Even with all the breakthroughs like AI, quantum computing, and what seems to be like a new technology appearing every day, the surprising truth is every piece of modern tech still speaks the same language it did decades ago, ones and zeros, or what you may know as binary. And binary is still the backbone of computing. But even though you may have heard of binary, a lot of people don't understand what it is or why computers even use it. So before we talk about how binary pertains to computers, let's explore what binary really is because it existed long before computers. Binary is simply a system of counting, and its earliest use was to represent logic, such as true or false, using a 1 or 0. And to help you understand further, let's look at a few other counting systems people have used over the centuries. The earliest form of counting was the use of tally marks. The way tally marks work is each notch or line represents an item, and usually every fifth mark was drawn as a diagonal to make counting easier, just like how we use groups of 5 today. The problem with using tally marks is the system becomes inefficient as the numbers get larger. Now, tally marks worked well for a time, but as civilization developed, people needed more efficient systems to count, measure, and trade. So early societies began developing numbers as a way to keep track of quantities. Some of the earliest systems were developed by the Sumerians, who, in a nutshell, used a base 60 math system, of which is still used today with the way we keep track of time and the 360-degree circle. As time progressed, the Romans used a counting system that used letters to represent values. Now, the problem with these systems is they technically didn't have a placeholder for 0. So let's fast forward in time by about 1,000 years, and a new numbering system was invented in India and then refined by the Arab mathematicians, which used the numbers 1 through 9, along with a big breakthrough of developing the number 0 to represent blanks, which gave us the numbers 0 through 9, which we now know today as base 10. Base 10 is the number system we use every day, where each digit's position represents the number of tens you have, like ones, tens, hundreds, and thousands. So, for example, the number 328 means you have 3 100s, 2 tens, and 8 ones. This positional numbering structure makes math faster, easier, and more scalable. Instead of using new symbols for bigger numbers, like the Romans did, we just add digits to the left, with each new digit increasing the value tenfold. So just how base 10 uses 10 digits, 0 through 9, and base 60 used 60 symbols, binary is simply a base 2 system, meaning it only uses 2 digits, 0 and 1. The rest works the same way when you count, and counting in binary looks like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if you're like me, thinking in base 2 math might give you a headache, so we'll move on from that. But that still begs the question of why did the first computer creators use a base 2 system instead of base 10 when base 10 math is clearly a better system? Well, the answer is base 2 was used out of necessity because of the technological limitations of the time. Put another way, base 2 was used because early computers had extremely limited tech. Using binary made sense for speed, simplicity, and accuracy. You see, the goal of the first computers was to perform calculations faster and more accurately than humans, especially for things like military and scientific work. The first computers were the Z3 and Colossus, yet one of the first large-scale programmable digital computers was the ENIAC that was made in the United States, built at the University of Pennsylvania, and completed in 1945 and is still there today. These early computers used vacuum tubes because they were the first electronic components capable of acting like switches, turning electrical signals on or off, and much faster than mechanical switches or relays. Here's a fun fact. One of the problems with vacuum tubes is they would attract insects and needed to be cleaned, which is where we get the term debugging from. Eventually, these vacuum tubes were replaced by transistors, which are just tiny little switches that have 2 positions, 1 for on and 0 for off, which perfectly matches the binary system. Going one level deeper, in simple terms, a single transistor stores what's known as a bit, which is short for binary digit, and a binary digit is a unit of data, either 1 or 0. So yeah, those early computers were good at handling calculations, but that led to the question of how do you deal with letters, punctuation, or symbols when all you have to work with is ones and zeros? Well, engineers got to work and they figured out a way to string 8 bits together, which is known as a byte. One byte can hold 256 values from 0 to 255 using combinations that range from 8 zeros to 8 ones. From that point, they quickly figured out that these values were more than enough to represent all the letters in the alphabet, punctuation, numbers, simple commands, and even non-printing characters. And this breakthrough shaped everything. So now that letters could be assigned unique binary values, they just needed a system that converts letters into binary, which led to the development of a system called ASCII, which is short for American Standard Code for Information Interchange. And in simple terms, ASCII assigns a decimal or base 10 code to a number, letter, or special character, and that code is eventually converted into a binary number that computers can understand and process. To give you an idea of how ASCII works, here is a breakdown. In a nutshell, ASCII breaks everything into groups, then assigns the decimal value and binary numbers to the items in the group. For example, the capital A has the ASCII code of 65, which converts to this number in binary. Capital B has the ASCII value of 66, which converts to this number in binary. Capital C has an ASCII value of 67 and converts to this number in binary. Now, over time, as computers spread worldwide, we needed a way to include more languages and symbols, and ASCII wasn't enough. So in the early 1990s, Unicode was designed as a universal character set that includes every character from all the writing systems on Earth. Now, changing gears a bit, in the grand scheme of things, despite our current advances in technology, on or off is still the raw building blocks of everything digital. Without them, modern computing wouldn't exist. Every letter, color, sound, and image you see on a screen today is really millions or billions of tiny on-off signals working together, all of which stem from the millions of transistors switching on and off. Now, to give you an idea of how technology has progressed, what started off as 1 byte or 8 bits at a time eventually moved to 2 bytes or 16 bits, then 4 bytes, 32 bits. Now, many systems use 8 bytes or 64 bits. Just to give you an idea, 64-bit gives you the ability to handle 18.4 quintillion values. As we fast forward to today, with all of the advanced apps, to the games we play, our photographs, and media, everything still relies on billions of these tiny transistors working together, all flipping between on or off, and it's just ones and zeros at the core. Now, what about quantum computing? Quantum computing uses qubits instead of bits, which in simple terms can represent 0 and 1 simultaneously. But even with this big leap forward, quantum machines still rely on the classic binary system to control and interpret their results. So by now, it's clear this video could go on for a very long time. But what's important is that binary isn't some outdated relic. Binary still remains the universal foundation, and it's the timeless language of computers because it matches how every pixel on your screen, every sound you hear, and every response you get boils down to billions of tiny switches saying yes or no, on or off, ones and zeros. We hope you've enjoyed this video. Feel free to leave a comment and also like, share, and subscribe.